Welcome back, everyone. Lesson 5 is an introduction to integrals, and in this section we will first view integration through the lens of area. Then, we will discuss how to integrate functions by taking antiderivatives. What is the area between function f and the x-axis over the interval 1 to 5? This area can be found by integrating function f over this interval, but because it is a linear function, we can find this exact area with geometry. The total shaded area is 12, and it's important for you to understand that this is the value of function f integrated from 1 to 5. But what is the area between function g and the x-axis from 1 to 5? This shaded area is equal to function g integrated across the interval. However, we won't be able to use geometry to get this exact value. Instead, geometry would only allow us to approximate this area. And one way to approximate this area with geometry is by using rectangles under the curve. The area of each rectangle can be found through a base times height calculation, and the total area would be the sum of these areas. When asked to use rectangles, like the ones we just saw, to approximate the area under a curve, we might need to use left endpoints to construct them. How would we perform a left endpoint approximation to estimate the shaded area from A to B using only two subintervals? We would first need to divide the interval into two equal parts. Then we would identify the two subintervals, acknowledging the fact that each subinterval has a left and right side. Since this is a left endpoint approximation, we will use the left side of each subinterval to construct rectangles under the curve. Find the function value at the leftmost x-value of each subinterval. This function value establishes the height of the rectangle. As you can see in the diagram, the height of this first rectangle is the function value specifically when x is a, and the base of the rectangle is the length of the subinterval. Now we just need to repeat the same series of steps for the second interval. The second rectangle has a height that is equal to the function value when x is c. You can see that the heights of both rectangles are found by using the left endpoints of their respective subintervals, and that's why this is called a left endpoint approximation. We could construct these rectangles using right endpoints instead. We would still acknowledge each subinterval, this time identifying their right endpoints. Each right endpoint helps us find the height of each rectangle. The first rectangle would have a height equal to the function value when x is c. And this is because c is the right endpoint of the first subinterval. Similarly, b is the right endpoint of the second subinterval. So the function value at this location establishes the height of the second rectangle. Both rectangles have heights found by using the right endpoints of their respective subintervals, and this is why this is called a right endpoint approximation. Now, what about a midpoint approximation? Each subinterval not only has a left and right side, but also a middle, and we will use this middlemost point of each subinterval to find the heights to our rectangles. Still, each rectangle will span across the entire subinterval, going from the left endpoint all the way to the right endpoint. The middle of the interval only helps us determine each rectangle's height. And because we are using the middlemost point in this way, this is called a midpoint approximation. A trapezoidal approximation would use trapezoids instead of rectangles. A trapezoid can be created across each subinterval, and we would use the left and right endpoints to do this. The function values at each endpoint reflect the bases of this trapezoid, and the length of the subinterval reflects its height. With these components, we can calculate the area of the trapezoid, following its area formula. We would need to follow this procedure for every subinterval. Interestingly, the trapezoidal sum can be found another way. The trapezoidal approximation can be made by averaging out the left and right endpoint approximations, which use rectangles, not trapezoids. If function f is positive and decreasing from a to b, would a right endpoint approximation for the given integral be an over or underestimate? Remember that this integral would give the exact area of the shaded region. But the right endpoint approximation would lead to an underestimate of this area. Just looking at one rectangle across the interval is enough proof for us to make this conclusion, because the function is purely monotonic. Please pause the video to find a left endpoint approximation for the given integral using 4 equal subintervals. Were you able to correctly identify the 4 left endpoints? And did you get their respective y values? The left endpoint approximation should come out to 34. Now, pause the video to repeat the problem using right endpoints. Did you find the 4 right endpoints and their respective y values? The right endpoint approximation should come out to 26. Please pause the video to repeat the problem one more time, this time using a midpoint approximation. Did you correctly find the 4 midpoints and their respective y values? The midpoint approximation should come out to 31. What if we had to repeat this problem again to use 5 subintervals for a midpoint approximation? This is a little trickier because the numbers are harder to work with. We will need to divide the interval into 5 equal parts. Since the length of the interval is 4 units across, we will divide it by 5 to find that the length of each subinterval is 0.8. This means that 0.8 is the base of each rectangle in this approximation. However, we will need to work our way a half step into each subinterval to find our midpoints. Here are the midpoints to our subintervals. We now need their respective y values. To find each y value, plug x into the equation 10 minus x squared. Remember that these y values establish the height of each rectangle. We are now in a position to calculate every rectangle's area. It is the sum of these areas that gives us the midpoint approximation. Adding all 5 areas together gives 30.88. When we use rectangles to make area approximations, we should observe that the approximation will get more and more accurate with the inclusion of more rectangles. Furthermore, if we were able to include an infinite number of rectangles into any one region of space, it would give us an exact area. And this is what an integral is. A definite integral is the sum of the areas for an infinite number of rectangles. The integral sign itself looks like an elongated s, and this s stands for sum. The indefinite integral is an integral without any bounds. It is a function that signals an antiderivative. In prior lessons, we focused on taking derivatives, stepping down to first, second, and higher-order derivative functions. In this section, we will discuss how to move in the opposite direction. Taking antiderivatives brings us up closer to the original function. For example, the derivative of x squared is 2x, and the antiderivative of 2x is x squared. Let's learn the basics of antiderivatives. Here's what you should know. The antiderivative of the constant k is k times x plus c, and the antiderivative of x to the nth power is x raised to the n plus 1 power, divided by n plus 1 plus c. Let's use these 2 rules of antiderivatives in question 48. Part A asks for the antiderivative of a function with 2x terms and a constant. We can use power rule to integrate each x term. To do this, we must increase the current power by 1, then divide the term by the new power. The constant must get multiplied by the variable. Then we can simplify the expression and add c. You should recall the derivative rules for the 6 trigonometric functions. This can help you take antiderivatives. For example, since the derivative of sine is cosine, the antiderivative of cosine is sine. If you know these derivatives well, then you are in a great position to take antiderivatives. Make sure to have these rules memorized before moving forward. Question 49. To find the indefinite integral given in Part A, we should first expand out the integrand into multiple terms. After this expansion, we see separate terms that are the known derivatives of tangent and secant. The final answer is tangent of x plus secant of x plus c. We should also know how to find antiderivatives of exponential functions, as well as recognize the derivative of ln of x. The antiderivative of 1 over x is ln of x plus c. Note the absolute values around x in this situation. Question 50, Part C. To integrate this function, we will first need to rewrite the integrand. If we write the numerator as x minus 3 plus 3, we will be able to separate the fraction, which leads to two separate terms that can be integrated individually. The first fraction simplifies to the constant one, and the second is 3 over x minus 3. The final answer is x plus 3 ln of x minus 3 plus c. The U substitution method can be used to simplify an integrand with a change of variable. It also helps us stay accountable for the chain rule aspect of derivatives and antiderivatives. In question 51, we can say that u equals x cubed plus 1. Its derivative, du, equals 3x squared dx. We can now replace the longer expressions of x with u and du where appropriate. As a result, the integrand becomes u to the fourth power, and this can be integrated with power rule. The final answer is 1/5 times x cubed plus 1 raised to the fifth power, plus c. Here's another example. The integrand in Part D shows an inner function of 3x. It is this inner function that should be represented by u. The derivative reveals that dx equals 1/3 of du. We can now make substitutions to completely rewrite the integrand in terms of u and du. The result is a simplified integral with a clear antiderivative. The final answer is 1/3 times tangent of 3x plus c. Now that we know how to take antiderivatives, we are now in a position to evaluate definite integrals, which are integrals with lower and upper bounds. To evaluate a definite integral, we should first find the antiderivative. In Part A, the antiderivative can be found with power rule, and it's 3x squared over 2 plus 2x. Next, we need to plug in the upper and lower bounds into the antiderivative rule and subtract the two quantities. This is an upper minus lower calculation. The final answer is 37.5. Investigation 21. To find f of 8, we should use the first fundamental theorem of calculus, which states that a definite integral can be evaluated with the antiderivative of the integrand. The upper minus lower calculation that follows equals the value of the integral, which in our case is 7. This equation shows us that f of 8 must equal 17. Investigation 22 is designed to help you understand the second fundamental theorem of calculus. If we take the antiderivative and follow up with an upper minus lower calculation, we find a new way to express g of x. And we can find the derivative of g of x, taking the derivative term by term. We just need to be mindful of chain rule as we take each derivative. Here is the rule for g prime of x. And what I want to bring to your attention is that taking the antiderivative is actually an unnecessary step. The derivative rule can be found by plugging in the bounds into the integrand and multiplying by the derivative of that bound. Here's an example. In Part A, the upper bound is 0, which is a constant, and all constants have derivatives that are equal to 0. This means that the starting term of g prime is 0, and we will now follow up with subtraction for the lower term. The lower term is 2x, so we will plug this into the integrand and then multiply by its derivative of 2 to complete the chain rule aspect of this problem. The final derivative can be rewritten as follows. Here are a few properties of definite integrals. The first one is the additive property, which tells us that an interval can be subdivided into two or more parts, and the total value of the integral will be equal to the sum of all the integrated subintervals. In other words, the total is the sum of its parts. And each part can be represented as its own integral. Ultimately, adding the integrals for each part yields the integral over the entire region of space. Other properties of definite integrals include the following. Number 1. Coefficients can be moved outside the integral. If we are to integrate 5x squared, we could move 5 out in front of the integral.
Number 2. Terms that comprise the integrand can be fully represented by their own integrals.
In other words, we integrate these terms separately. This integral, for example, can be separated into two, one for x squared and one for x. Lastly, flipping the bounds of a definite integral gives a result that is opposite in sign. And a definite integral with identical upper and lower bounds is always 0. Question 54 asks us to find a definite integral of function f. The bounds of this integral show that it is only part of a larger integrated region. According to the additive property of integrals, the parts must add up to the whole. As a result, x plus 8 must equal negative 17, making the answer negative 25. In question 55, we will have to separate an integral across all of its terms. The integral in question has 3 terms, so we can write each one with its own integral. Additionally, we will also be able to take the coefficient of 4 out of the first of these new integrals. Once we have rewritten the original statement, we can bring in the known values for the first 2 definite integrals. The last integral can be evaluated with geometry, or by the first fundamental theorem of calculus. Either method should show you that our last integral has a value of 4. In total, we should get a final answer of 31. Question 57. What is the value of function g when x equals 0? When we plug in 0 into the function rule, we see that the upper bound of the integral is 0 and the lower bound is 4. We can flip these bounds if we remember to negate the integral, and we can then evaluate the integral using geometry. Keep in mind the areas under the x-axis should be viewed as negative quantities. With this in mind, we can calculate the positive and negative areas separately. You might even recognize places where the positive and negative areas would cancel each other out. The final answer is that g of 0 is negative 4. What about g of 11? Would you be able to find the value of function f integrated from 4 to 11? This amounts to finding the area between the curve and the x-axis. This entire region lies above the x-axis, so every area should be given a positive value. The region in yellow looks to be formed using the lower half of a circle, and the region in green is a right triangle with an area of 3. It is the yellow region that is tricky to calculate. One way to view this part of the graph is as a rectangle that has a semicircle taken out of it. To find the area in yellow, we can take the full area of this rectangle and subtract out the area of the semicircle. Since the semicircle has a radius of 2 units, its area is 2 pi, and the area in yellow can be expressed as 8 minus 2 pi. The final answer is that g of 11 is equal to 11 minus 2 pi. Investigation 23. Can you find the area bounded by the given curves? This area in yellow can be tricky to calculate. However, it can be done several different ways. One way to find this area is to consider the image of a full rectangle over this space. This full rectangle has an area that can be found through a base times height calculation. The area of the entire rectangle is 8. Next, we need to remove the missing portion of the rectangle, which is the area under the curve y equals root x. This area must be found using a definite integral. Yet this isn't the only way to go about tackling this problem. Another approach we could take is with an integration with respect to y. When we integrate with respect to y, all quantities should be represented with the y variable, including the bounds of the integral. The yellow region contains y values ranging from 0 to 2. This makes 0 and 2 the lower and upper bounds of the integral. Next, we need a way to represent the changing lengths within this region of space. These lengths change with the y values and are equal to the corresponding value of x. Since x equals y squared, we should integrate y squared from 0 to 2. Doing so yields the desired area, which is equal to 8 over 3. Thanks for watching this introduction to integrals. Hope to see you again in our next lesson.